Welcome to the Society of Wetland Scientists webinar series. We are so glad you could join us today. My name is Jody Burns, and I'm co-chair of the SWS Webinar Series Planning Committee. As a longtime SWS member, I am pleased to be today's moderator for the webinar. We are excited to share this SWS e-learning experience during a time when many of us are looking for virtual opportunities to stay engaged and connected and gain continuing education credits during any of our challenging times. Today's lecture and topic will be unexpected results in adaptive management. It is my distinct pleasure to introduce our speaker today, Christa Zweig. Christa Zweig is a wetland landscape ecologist with the South Florida Water Management District and has worked in the Everglades for 22 years. She received her Bachelor of Science from the University of Richmond in Virginia and her master's and PhD from the University of Florida. Her master's work focused on body condition of the American alligator and her PhD on the vegetation ecology of the Everglades ridge and slough landscape. Currently, her focus is conducting applied science for Everglades restoration. Welcome, Christa.
Thank you very much. Sorry. Let me get my screen started. Thank you for having me here today. I'm excited to share some of our research that we've been doing down in South Florida Water Management District. Here is the Everglades to the left. It was the past, in the past, it stretched all the way from the Kissimmee chain of lakes near Orlando down to Florida Bay. The present you see on the right is what it is now. It's about 50% of the extent it used to be, and it's a compartmentalized system. This is the restoration of the Everglades, a map of the restoration of the Everglades. There's things, I'm going to say a lot of acronyms, SEP South, SEP North, SEP New Water. It's all about getting the water right. But we don't really know what happens when we get the water right, because there hasn't been, part of the restoration is not just getting water depths right, but returning flow to the landscape. And there hasn't been flow in the Central Everglades in over 40 years at the most, at the soonest. So the Decomp Physical Model was set up to answer these questions about flow, nutrient loads, levee removal, and canal backfilling. It was a Baki design. There was a structure put in over here on the western levee, and then there was this flowway with the historic flow path over to a canal where they did 3 backfill treatments, full, partial, and none. And then they removed the levee here so water could flow across the landscape. This is the first flow day. It was a historic day. That's the first time flow had been on the landscape in a really long time. We woke up extremely early. Helicopters were in the air, tiaras were worn, crowds were gathered, and dye was in the water. But things didn't go as planned. This is the structure. And this is the way water flowed. This is the historic flow path. It's kind of a southwest to northwest to southeast flow, the purple line. That's where all of the monitoring had been set because that's how we thought it was going to go. But instead, most of the water flow went with this green line over to the canal and down to our treatments. So with this unexpected results, we wondered what we could do to change the direction of flow. And one of my ideas was to get rid of the resistance of the vegetation in the way. So we wanted to see if we could change the direction of flow. Could we increase flow speeds? Because also from the historic flow speeds of the Everglades were 2 to 5 centimeters per second. And that historic flow speed only really extended about 500 meters from the structure. So could we get those flow speeds, those historic flow speeds, to get further into the DPM footprint? We wanted to know if we could create microtopography, because there is a difference in elevation between the ridges, which are sawgrass ridges, a little bit higher, usually about 20 centimeters or more higher than the open water sloughs. And we wanted to know, which is very important for the creating the structure of sloughs, could we actually create this differential flow through ridges and sloughs through our active management? And I call it brute force science. That's the kind of science I do. Nothing with glassware or things that can spill. So with my dissertation work, I'd done a lot of cutting of marsh samples. So I was like, we can just cut the sawgrass and get it out of the way. And that's actually what we did. That's about 100 meters. Do you see in front of you? We just started and started cutting. It was really, really difficult. So, you know, this was our idea at first, but then we realized that wasn't actually an answer to what was happening. But we did actually redirect some flow through this channel, and it was very fast through that channel. You can see it here on the landscape. In the background is the structure. And so the water would come here, and it was flowing like this way, but we got to bend a little bit more north. It's not necessarily the direction we wanted it to, but it was where we had a chance to do this active management. So because it was so intensive, we decided to see if we could do a smash slough, we called it. We used airboats to extend the cut slough from one slough to the next. The smash slough was not as successful. We didn't really get faster speeds, and it really wasn't as permanent as cutting. So we realized getting rid of the vegetation resistance would allow us to change the speed of the water flow and the direction of water flow, but how are we going to do that at a landscape scale? And just to make sure, oh, here's the elevation actually of that area, and you can see the structure here, and the water is actually following an elevation gradient. And it's hard to get water to go against an elevation gradient, so we wondered how could we do that, so that idea was to change the vegetation resistance and see if we could bend it away from that elevation gradient. And so before we did that on a landscape scale, I did a model on EFDC, which stands for Environmental Flow Dynamics Model, model. And so the inputs to this model were elevation that we had on the landscape, overall landscape flow vectors that we had from dye. We had SF6 tracers and flow tracker data. We had depths and velocity data at certain points to use as to look and make sure the model was correct. Inputs through the S152, outputs through the levee gap. We had estimates of seepage from the levees, and then drag coefficients from sawgrass from the literature. So we did this model, and we did it with and without the active management, where I took out the resistance from the sawgrass. And the flow velocities weren't quite the same as they are on the landscape, but what they were is twice as fast in those vegetation areas where there was less vegetation resistance than they were outside the active managed areas in the model. And this is a validation from actual data and the modeling. The model is the dashed line, and the actual is the solid line. It followed one of the pulses that you can see in the actual data. There's a second pulse that wasn't modeled. Well, it modeled the second pulse, or the first pulse, very close to the actual data. So we decided, okay, the model works. We have some validation to do this on the landscape. Now, what are we going to do? And we actually took a clue from some other work that had been done in the Everglades. And I went back to the 1940s imagery and traced out where there were sloughs that there weren't anymore. And I traced those out on GIS and then put them on the landscape. And we used glyphosate to get rid of the sawgrass. And this is what it looked like on the landscape. You can see it. We went with the contours of the old sloughs. We even had a dead end slough like it was back in the 40s. That's what it looked like afterwards. We actually were pre-AMI these sites. We had historic flows up to this first site and a little bit towards the second site. We actually got flows up to 15 centimeters a second at the first site 2 now. We actually slowed flow down, or about the same at site 1. And then we propagated historic flows about 1,200 meters from the structure now instead of 500 meters. So we more than doubled the distance away from the structure that we were able to have historic flows. And then we also wanted to look at the difference between those sprayed areas and the ridges that they used to be, because we want them to function as a slough. And we looked at a few things. We looked at dissolved oxygen. Dissolved oxygen actually recovers pretty quickly once you get rid of that canopy. The flock production and flock transport was still kind of ridge-like, but there was still a lot of dead material that hadn't decayed in the water column. The species actually reacted fairly quickly because the ridges in this area, they weren't super thick. So there were actually still some crinum lilies in there still, and some ecologically, and so the species were able to recover pretty quickly, and it was more slough-like. And the decomposition, as of the time we were looking at it, it was kind of in between a ridge and slough decomposition rates. This is my video of that ridge or the Amy area. You can see there's a lot of dead material, but the thing that we noticed first, and it's hard to not notice, is there's all this periphyton that had grown on the dead material. And periphyton is really important in the Everglades for sediment creation, for oxygen production, and for food, for snails and other things. So you can see there's quite a bit of periphyton in that area on the dead stems. In fact, probably more than there is in an actual slough. And this is another picture of the periphyton crust on the top, just because I think it's beautiful. And when this was first done, it looked pretty destroyed, you know, because all of the dead material. So I was happy to see life at some point. So here is a picture. Actually, you can see some of the dead stems still sticking out, but it's you can see the crinum lilies and maybe Hymenicalis sticking, growing out of the open water. And this is the slide just to show you what it looks like now and to go over the results of the project. And could we change the direction of flow? Yes, we did. In fact, when the flow used to be about 75% straight east and about 25% with the historic flow, now we're approximating it's about 50-50 east and with historic flow. Can we increase flow speeds and propagate it further into the DPM footprint? Yes, we could. We at least doubled the area of marsh that was under historic flow speeds. And we actually sped it up quite a bit in the parts closer to the structure. We wanted to know if we could create microtopography. We're not actually quite sure on that yet because it takes a little bit longer to develop. And then could we create differential ridge and slough flow? And that is, we did. In the areas where there was the Amy treatments, they were actually, the flow through there was faster than in the ridges. So we were able to kind of recreate these 1940s sloughs using herbicides to open up the area. Actually, in this area, and unlike others, we actually used airboats to smash the dead material down, but that was also very intensive. So we haven't done that in the future Amy treatments. So in the Everglades, I have this quick video. It's a little too long. I'll probably stop it before it goes. Sediment grows plants. We have this cycle. Sediment grows plants, and plants create sediment, and sediment is redistributed through flow to then make the microtopography in the landscape that kind of propagates this ridge and slough landscape. But our unexpected result from the DPM was that these flows actually cause a collapse of these periphyton communities that are really important. So this is the same slough before on the left and after, flow has been going for a little while. So it's not just, and this is with flows coming through the structure weren't allowed to be more than 10 parts per billion because that is what was considered enriched. Anything over than that, and we didn't want to contribute to the enrichment of the Everglades. So the stuff coming through the structure was actually the proper phosphorus load, and phosphorus, increased phosphorus can cause periphyton to collapse like this. But instead, it could be partly the increased load, but also the mechanics or mechanical destruction of the periphyton from actual flow. So you can see here that it kind of creeps along over time. It takes about 3 to 5 months to clear a structure out, but you can also see the animals are helping as they go up and down here. It helps the flow kind of infect through these areas. So if flow equals less periphyton and less submerged aquatic vegetation, the story that we know about the Everglades that we all know and love, that landscape flows from about 2 to 5 centimeters from Lake Okeechobee over the berm to Florida Bay, that would actually create a sediment-starved system. So we had to stop and think about, okay, how are we going to think about this differently now? And how do we fit this new information from DPM into the Everglades story? Well, a big part of the Everglades story is also its dynamic nature. Seasonal flooding, El Nino, La Nina, decadal climate oscillations, hurricanes, regular climate variability, you name it, we've got it. So the key is in the dynamics on this landscape. And so the ridge and slough pattern isn't just one big striated river. There are a lot of isolated sloughs or dead ends, where even if flow is on the landscape, those areas would have still slow to no flow. So you can see here, this is my elementary diagram. You can see here where sediment is very sparse, where there's flow, and then where areas where there's sediment rich with no flow. So our hypothesis was, here's the no flow and here's the flow, or here's the flow areas. Our hypothesis was spatial and temporal dynamics in flow and SAV and periphyton cover create a stable landscape. So we had to think about how that would happen. So in a hurricane and a flood would come, and in large pulses, they would actually redistribute that sediment into areas that didn't have sediment created because they had too high flow. There's also wind-driven disturbance where those areas that have no flow and a lot of sediment created, that gets redistributed. Hurricanes are just other wind events. So we had a temporal hypothesis that spatial and temporal dynamics in flow and SAV periphyton cover create this stable landscape. So some years you'll have less water, as in over here, and more periphyton. This is 3A, Conservation 3A South in the Everglades. And over here you have more water and less periphyton. So there's more flow through here, probably less periphyton, less water, more periphyton. And how we needed to represent that in a model. But because I'm not an engineer, I based the hydrologic and plant interactions on an infectious disease model. So flow kind of equal to infectivity. The faster the flow, the less periphyton and SAV can resist, the more it would infect into the landscape. So I made this model. Sorry, the thing is covering my slide there, so I can't really see. Time also affects resistance. So like you saw in this slide I showed before, over time, the erosivity of the periphyton actually increases. So we've had that in the model as well. This is a 30-meter scale from Landsat imagery. We have ridges and sloughs in the Everglades, actual ridges and sloughs. We started with that as our configuration and mimicked different hydrologic cycles. So we had, I had to actually change it because like the DPM, when I put flow into the top of this model, flow only actually went faster a certain distance from the model, from the flow introduction. So it was kind of nice that it reflected reality, but it was also kind of annoying because it wasn't allowing me to work this model in as much of the landscape as I had hoped. So I did several configurations. I did original landscape, kind of like this. I did one with no dead ends, so no areas for sediment to be created. I did 1 or 2 dead ends, but the results for this, I make it easier. I'm just sticking to the original landscape with dead ends or no landscapes, or sorry, no dead ends on landscape. And so I ran this model to see which configuration creates a stable landscape, and then how many dead ends or isolated sloughs do you need, and what hydrologic cycles creates a stable landscape with these. Like, what is the wet dry cycles and duration? So here's where the model actually had to go down to. Flow only extended to a significant degree about 1 kilometer from where flow was introduced. So we had to simplify the landscape into smaller sections. And then we even actually had to section it out into 1 kilometer from the flow structures in the model, where the highest flow happened, and then another kilometer where we did still have flow, but it was much slower. And the results were a lot of ugly box models, box plots. So I actually kind of just cartooned them so it would be easier to see. Within the 1 kilometer from the flow where you had the highest flows, I did an annual wet dry cycle, and then also looked at a decadal wet dry cycle. And for this, you have, if there were no isolated sloughs, the amount of sediment created was actually very little, and it actually over 100, as you get faster, less sediment was created. You didn't really have much sediment created on the landscape the faster you went. It actually bottomed out at 0. And then if you have isolated sloughs on the original landscape, you can get up to 100 centimeters a second in your flow rates before you actually bottom out at 0 sediment created. And then it was actually not quite as drastic on the annual scale, but on the decadal scale it was. And then this is the second part where there wasn't quite as fast flows, but there were still some increased flows that second kilometer away from the structure. If you had no isolated sloughs, you still get some sediment created even with high flows. And I think that's just because, that's a good question. I think that's because the 100% or the 100 centimeter flows were actually the 100 centimeter flows coming from the structure. So you still don't have faster flows in that second kilometer as you do in the first kilometer. So that's why there was still sediment created. And then in the original landscape, you didn't have any decrease in the sediment created, no matter how fast you had sediment or you had a flow coming out of the structures. So, sorry about that. So having areas of little or no flow in the landscape was very important to actually creating the sediment needed for the landscape maintenance over time. And so why does this matter, really, this model matter? When flow was introduced back to the landscape, this SPF model, when it is introduced back to the entire landscape, this SPF model can provide guidance as to where to put it and how much flow to put in. And then when active management is used on the landscape, this SPF model can provide guidance on how complex and this restored landscape has to be. Do we need to make it exactly like it was in the 1940s, which even still is altered? Or can we actually make some flow channels that are a little faster than others? And that's it. It actually went quite a bit faster than I thought it was going to do. So if I have any questions, I'd be happy to take those.
All right, thank you, Christa, for that interesting presentation. We do have a couple of questions here. One of our viewers asked, were you worried about cattails colonizing areas where sawgrass was treated?
We were in areas that have been closer, that are closer to the structure. DPM is actually seeing enrichment, like above its 500 milligrams per kilogram, I guess, in the soils. We're seeing enrichment in those areas closest to the structure. We actually have a flume study going on right now that kind of gets at, is it flow speed or TP load, and it's a little farther from the structure, so we can manipulate flow speeds, but with the same phosphorus levels. So that is some, we were concerned. We did actually have to go in at some point and use active management again to keep the area open from cattail just near the structure. Luckily, there is a different herbicide that you can use that actually targets cattail instead of sawgrass. So we're able to, when there is cattail there, we're able to at least target it. But yes, I mean, that is actually the reason why we're continuing the study with the flume, and also hoping that it can really inform the next steps of the restoration, like step south and step north, when they're putting all this flow onto landscape. How would be the best way to, what's the best configuration for putting this flow back in the landscape so we don't cause those issues with cattail?
Okay. And again, I forgot to mention, I'll be posing any questions that I received through the Q&A button to the presenter. If you forget to ask a question or have to leave before the Q&A is over, you can email the presenter at the email address listed on this slide. Another question we have is, in addition to species, what was the other metric that was slough-like in your preliminary results?
I think that it was a flow speeds probably, and then a decomposition was kind of in between. So we did have slough-like flow speeds in those AMI areas, as well as oxygen production.
Okay. Another question we have is, how long did it take for the vegetation treated with herbicide to recover, and how long did the effects of that treatment last?
I was actually curious about this too, because I hadn't dealt with much herbicide before I came here to the district. And when you spray cattail, it recovers very quickly for the most part, you know, after a while. But sawgrass, especially with glyphosate, it doesn't. It is done and killed, and the only way for it to recover is to growing from the sides. So the, you know, our sloughs are still very open. They don't have any sawgrass regrowth. Actually, that the cut slough, the Zweig slough, that doesn't have a ton of sawgrass regrowth either, because, and that was one of our hopes, is that when you have the flow going through there, it might inhibit sawgrass growth out into the flow area. And it looks like in the cut slough that it did happen. I haven't seen a whole lot of regrowth back into the slough, because that'll take a lot of time for sawgrass to get back in there. But yeah, it wasn't something I was as familiar with. And since it's not cattail, we have a lot more success.
Another one's come in. Does the change in stream flow have any impact on the downstream side? And how do you consider the upstream downstream relationship in your research?
I guess I'm not sure which upstream, what you mean by upstream and downstream.
Maybe they mean upslope or downslope from where you
I guess, could you ask the question again? So with knowing that, thinking about that way.
I'm not exactly sure either. So it says, does the change in stream flow have any impact on the downstream? And how did you consider the upstream downstream relationship?
It does have effects on the downstream if we're thinking about from the structure. The effects it has for the most part right now has been some nutrient enrichment, and also hopefully the opening and staying open of those sloughs that we've created. The upstream of that is a canal, so we weren't as concerned about the upstream part of that. If you're talking about upstream just within the project area, the upstream is taking the brunt of the nutrient enrichment. We're hoping, and it seems to be traveling. I can't remember the speed that the nutrient enrichment is traveling, but it was approximated in about a decade that nutrient enrichment would be across the entire landscape, and maybe down into some of the other areas that they've opened up. So it is traveling, but it's I think because, you know, the wetlands, they can act as a kind of a sponge for the nutrients. Hopefully it's not as fast as it could be, but yeah, it is definitely impacting the upstream in the project area. The upstream of outside the project area is a canal, so we're not quite as worried about that.
Olivia Johnson asked, can you speak more to why you chose herbicide versus smash or crushing vegetation? Yeah,
the crushing and smashing does not last at all. It barely lasted a season, really. You know, I wasn't a huge fan of herbicide, but honestly, sawgrass is a pretty resilient plant to hydrologic conditions, which is why it does so well in a dynamic system like the Everglades. There are places in the Everglades that have been inundated for probably 30 or 40 years. There's still plenty of sawgrass there. it actually can like climb up its own itself. It's kind of it grows up its culms so it can stay above the water. So even though it might be thinner, it's still there. So our only really choice was to kill it, and cutting it was not. Even though I had great hopes, cutting it was not the way to do it. And yeah, the smashing just did not last.
All right, another question. How do you propose a balance of creating the dead end sloughs to increase sedimentation, but still have flow not short circuiting into the canal to the south?
Actually, one of the interesting things about DPM, that's a good question. And we're kind of having to think of it now on a larger scale because they're actually going ahead and in that same area, putting more structures in, and they're actually going to degrade that levee so that it moves down into a bigger area and down into Everglades National Park. But one of the things that I've come across thinking about this is you go and you read some of the historical accounts of the Everglades, and I'm really excited about this right now because I talked about this story that we've all heard. The Everglades is this, slow flowing sheet flow across the landscape through the sawgrass and sloughs. But the more that I get into it, because first DPM made us think like, no, that's actually not how it happens because it causes this collapse of periphyton. And you have to have periphyton and SAV in this system to have it look like it does. So you have developed the way it did and to be maintained. So we started thinking about it, and I've been reading some historical accounts, and they actually talk about main flow channels, basically, that are kind of open of SAV and any kind of water vegetation growth, and then others that are slow and not flowing. So it's almost like, we're starting to think about the Everglades more as like a river delta, and very dynamic in where that main flow channel is. We're thinking about having it move around on the landscape. What is actually a fast flow slough and what is not might change, and then that is kind of works along with that idea that you have to have some slow and you have to have some fast, and where that happens I'm not sure. And actually I'm working on a model right now to kind of look at that, not just moving the fast flow around on the landscape like that river delta, but also looking at pulse flows versus the sheet flow. Like I actually calculated the amount of water that falls from one of our really intense summer rainstorms, and the CFS in that was like 14,000. Now the CFS coming out of our structure is 250 to 800. So the CFS coming out of a storm is a really big deal, to that area that it's over. And it might actually be the source of those pulses and that sediment movement that happens over areas that are slow. So I'm trying to, it's kind of I'm trying to do a model right now that kind of incorporates that. But dealing with vegetation, you make models that are more on like an annual cycle. But right now I'm trying to model pulses and flows that are not on an annual cycle. So that's where I'm having to kind of nest some temporal modeling that's been challenging to think about, but I think I'm there now. But yeah, it's been really exciting actually thinking about the Everglades in a different way than the story you were always told, and thinking about it. I mean, since I came here, they talk about the Everglades being dynamic, but I think it's even more dynamic than we thought it was. And that's really neat to think about as a scientist.
Mm-hmm. There's another flow related question that you might have covered just a bit, but what happens to the flow that slows down farther from the source? Does the ridge confine this flow or allow lateral movement through the soil substrate to dissipate this flow? Is that something that you've been able to figure out a little bit?
No, and I think it just, it slows down. I don't even think it really, I mean, it kind of piles up because when you put that, you open those structures initially, you do get a really, high increase in probably like 10 centimeters increase in water depth, like right away. So it does go into that area. It's only got so many places to flow through because of the ridges have actually grown in over time in that area. So you do see it kind of just backs up. And over time, you see it recede when you turn the structure off. So I think that's just what happens. But I'm definitely not hydrologist.
Okay, we have a vegetation related question. Is TIFA becoming established in nutrient enriched areas like the area near the structure? From your observations?
Yes, typhoid, you know, it's natural in the Everglades, and it's established in certain areas. I have my supervisor has a theory that it's where groundwater comes up and there's more sulfate and nutrients. But you know, that's always been in the Everglades, but in little pockets. I would say when cattail gets there, it's established. It is so resilient to treatment. I mean, we did some areas in one of the other conservation areas. We did some areas of treatments, different treatments. We did fire, and it grew back within a month or 2 months. It was thicker than before. They go out there with this herbicide, and you know, it hits it back, but it's very good at you know, sending rabbits out that might, you know, have survived a little bit, and you always see pop-ups coming in. So I would say as long as cattail's there, it's established. And yes, so it is there, so it is established. Yeah, and that's what we're worried about for other parts of the projects where they're putting in more structures and more flow, is that this is going to happen. How are we going to deal with it? And that's one of the things we're working on.
Was there any other information you wanted to share with our audience? I don't see any questions right now, unless someone.
I got to talk about my new model and the you know, rethinking of the Everglades. That's really what's been on my mind recently, and so that's what's exciting right now. And actually, I'll share this. I've been here for almost 10 years, and I work with some really amazing scientists here at the Water Management District. They started this kind of active management stuff before I came here. Luckily, they let me take the reins on it for DPM, but they do some really, really interesting work. So besides what I've told you here, there's a lot of stuff that they could tell you about that is really important to wetland restoration. And so if you all are interested, there are a lot of other scientists here at the district too, who probably would talk longer than I did, but have some really interesting results. Biogeochemistry is one that I don't really cover, and that they have a lot of information on.
All right. Well, thank you very much, Christa.
Thank you. If
we could move on to the next slide. We're proud to recognize our SWS webinar series sponsors for 2023, BioApp, Cattails Environmental, and Ducks Unlimited. You can find their information at the websites listed on the slide. Please visit, like, and follow our SWS webinar sponsors. Our next English webinar will be February 16th with a presentation on the Higman Barge Removal Wetland Restoration Project. And on March 15th, we'll have our next Spanish language webinar. Check out our website and social media channels to learn more and register for upcoming events. And don't forget to complete the survey that will be sent to you after this webinar to receive a certificate of participation and provide feedback to the committee on this webinar series. Thanks again to Dr. Zweig and to our audience for participating today. Have a wonderful day, and everyone stay well.
Thank you.